So for number 60, it's asking us to graph the sequence, which I did here using a software called GeoGebra. And then it wants us to determine whether it is convergent or divergent. And so we can see here that it does appear to be convergent, right? It does appear to tend to a specific value, and that specific value looks like it's 5. So we are going to say that AN is convergent. AN is convergent, and then it asks us to guess the value of the limit. So it does appear here that the limit is 5. So we're going to say that the limit as n approaches infinity is 5. And I'm just going to leave a question mark here because that is just a guess, right? So now what they want us to do is they want us to prove our guess. So we're going to have to go here, and we're going to have to try to find the limit. So the limit as n approaches infinity of our AN, which is going to be, that is going to be 3 to the power of n plus 5 to the power of n. And instead of the root n, I'm just going to put to the power of 1 over n. It's the same thing, but this is just a little bit easier to do math with. So now, if we evaluate this limit, it's going to be 3 to the power of infinity, that's just infinity, plus 5 to the power of infinity, that's infinity, to the power of 1 divided by infinity, that's 0. So we don't know what wins, right? We don't know if it's the base, that's infinity, that wins. We don't know if it's the exponent, that's 0, that wins. So we don't know where this heads to. And now this does look like an indeterminate form, but it's not quite. Right? Actually, it is indeterminate form, but it's not quite the L'Hopital form that we want it to be, because in L'Hopital we want it to be infinity over infinity, or 0 over 0. That's what we want. So what we're going to do here is we're going to try to find this limit, but now instead of it being with the sequence, we're going to try to find it with a function. So we're going to go the limit as x approaches infinity of 3 to the power of x plus 5 to the power of x all over 1 over x. So we're using the function y is equal to 3 to the power of x plus 5 to the power of x all over 1 over x. We're using this to find the limit of our sequence, because these the sequence and the function, they behave the same way. So the difference is that the function, so if I do this in blue, right, my function is going to connect all these dots, and it's going to be continuous. It takes on all the possible values for x, right, all the real numbers, whereas the sequence, as we can see, is just the dots. It's just evaluated at 1, 2, 3, and so on. It can't evaluate numbers between them, so like 1.5. But regardless, we can see here that both the sequence and the function, they all behave the same way, right? They head to the same place. So if we find the limit of the function, well, we know that the sequence is going to behave the same way, so that is also going to be the limit of the sequence. Okay, so once we're here, we're going to do this, and what we're going to do, our problem over here is this 1 over x, that's the exponent. Because it's like we're raising to 0. We're taking infinity and raising to 0. So we want to get rid of that exponent. And the way that we're going to do this is by taking the ln of both sides. So I have ln y is equal to ln of 3 to the power of x plus 5 to the power of x, all of this times 1 over x. And now, because of the log rules, I'm allowed to bring this 1 over x to the side, right? So I have that ln y is equal to 1 over x times ln of 3 to the power of x plus 5 to the power of x. Okay, so if I take the limit here, I'm going to take the limit of both sides. So on both sides, I'm going to take the limit as x approaches infinity, and then actually, maybe I'm going to just move this around so I can make more space. So I'm just going to move this out further, and then move this out further here. Yeah. So I'm going to take the limit of both sides. So the limit as x approaches infinity of ln y is equal to the limit as x approaches infinity of 1 over x times ln of 3 to the power of x plus 5 to the power of x. Okay, so once we take this limit here, on the right-hand side, we can see that this is going to be 1 over infinity, so that's infinity on the bottom, times ln, this is going to be ln of 3 to the power of infinity is infinity. So we're going to have ln of infinity, which is also infinity, right? So when we take this limit, we're going to get infinity over infinity, and that is L'Hopital form. That is exactly what we want. So we're going to use L'Hopital, and we're going to take the derivative of the guy on the top and on the bottom. And actually, let me just clean this up a little bit so that it becomes more obvious. Okay. So once we're going to use L'Hopital, on the top we're going to take the derivative of this guy, ln of 3 to the power of x plus 5 to the power of x. So that is 1 divided by 3 to the power of x plus 5 to the power of x. That's the chain rule, right? 1 divided by the argument times the derivative of the argument. So the derivative of the argument is going to be ln 3 times 3 to the power of x plus ln 5 times 5 to the power of x. And then on the bottom, the derivative of x is just 1. So once we have this, let's just clean this up a little bit. I'm going to move to the side. And this is going to be ln 3 times 3 to the power of x plus ln 5 times 5 to the power of x. And all of this divided by 3 to the power of x plus 5 to the power of x. Okay, so all we have done here is we have cleaned this expression up, right? And let's see how we can improve it here. Well, if I take this limit over here, this limit as x approaches infinity, I'm still going to have 3 to the power of infinity plus 5 to the power of infinity over infinity. That's not going to be very helpful. So what I'm going to do here is I'm going to divide the top and the bottom by 5x. So 1 over 5x on top divided by 1 over 5x on the bottom. And the reason that I'm doing that is so that I can isolate some of these and at least get a number, right? Because we're going to have a bunch of quotients. That makes everything better. So once we get this, we're going to get, this is the limit as x approaches infinity of ln of 3 times 3 to the power of x divided by 5 to the power of x. This is 3/5 to the power of x plus ln 5 divided by 5x is just ln 5 divided by 3 to the power of x divided by 5x. This is once more just 3/5 to the power of x, and then plus 5 to the power of x divided by 5 to the power of x, that is equal to 1. So when we do this, now when we take this limit, this 3/5 to the power of x, well, 3/5 is less than 1, right? And so whenever we have something less than 1 raised to the power of x, that is going to go, and we take the limit as x goes to infinity, that's going to go to 0, because it's like saying, okay, 3/5 times 3/5 times 3/5 times 3/5 infinitely. And so because all of these are less than 0, less than 1, it's like going 0.6 times 0.6 and so on, and that's going to go to 0. So once we do this, we have that this is ln 3 times 0 plus the limit of ln 5, it doesn't change, right, because it doesn't depend on x, ln 5 over, this is going to be just 0, 3 to the power of 5 is 0, plus 1, and this is equal to ln 5. So, sheesh, that was quite a lot, right? So what we found here was that the limit of this whole thing, if we remember, the limit here is ln of 5, right? But now remember that, and actually I'm going to, but now we have here that, okay, the limit as x goes to infinity of ln y, right, is equal to the limit of this whole thing. This is equal to ln 5. And now I don't want the limit of ln(y), right? I want the limit of y because our function here is y. It's not ln of y. So what we're going to do here is we're going to take base e of both sides. So then we have that here, if we take it base e, we have that e to the ln y. Actually, I'm going to just put this above. So we have here that the limit as x approaches infinity of e to the ln y is going to be equal to e to the ln of 5. And so what we have here is that the e ln, they cancel out. So we have that the limit as x approaches infinity of y is equal to e to the ln, it cancels out. So that is just 5. And so that was quite the long road that we had to take. But finally, we have proved that this limit here is equal to 5. And so once we have proved it, we can go ahead and remember that our guess was 5. And we're going to remove this question mark and just put a check. So that is indeed 5. We have proved it. And that is it. So remember that all we did here was we, instead of taking the sequence, we represented it with a function, right? Took the ln of both sides so that I could get rid of this 1 over x on top. Then took this limit using L'Hopital, and we found that the limit using L'Hopital was ln(5). So when we go back here, remember that we're at ln(y), but we don't want ln(y), right? We want just y. So we had to take base e of both sides, and then that gives us that the limit of y is equal to 5. And remember that y is just our function.